So click and close, put all distractions away. We got good stuff to talk about today. Kind of stretch your brains a little bit. We're going to talk about some higher level stuff, higher dimensional stuff, literally and figuratively. So what about something like this? You guys, you've been working on solving linear systems with two variables, right? And that makes sense. All the linear systems you've solved so far have involved x's and y's, and they've clearly involved two equations, two linear equations at the same time. If I graph either one of those two equations in any of the problems that you've been working on, they would be aligned in the xy plane. Agreed? Okay? So what about this? This is also a linear system with three variables.
Yay!
Okay, so if you see do you have a problem with that at all? Is there anything there that seems a little odd?
That there's three variables.
That there's three variables?
Kind of a tough one.
Okay, so how are you going to come up with the equation of a line involving three variables?
It's like elimination or like replacement. It's one where like you multiply it and then you get through the other one.
Okay, we can. There's going to be, the algebra is not that difficult. I'm going to teach you a technique for solving a 3x3 linear system algebraically. It's not a big deal. But before we even get into that, this is a little weird, right? What's that even mean? A linear equation with three variables. Like, let's just take.
Is it three-dimensional?
Yeah.
Yeah, it's three-dimensional.
Okay, so now we're getting somewhere. Okay, now we're getting somewhere. So let's just take the top equation only, and let's talk about this. Here we've got 2x minus 6y plus 9z equals negative 8. Well, where do z's come from?
That's the third axis.
The-
Makes it three-dimensional.
Say it again?
The third axis.
The third axis. Okay, so when I deal with stuff up here on the board, it's intrinsically a two-dimensional thing, right? Okay, when I write an XY plane on the board, it fits perfectly because the board is planar. So there's plenty of room on here for both an x-axis and a y-axis, right? Now, what's really important, before we jump into anything harder than this, what's necessary about the relationship between the x-axis and the y-axis? They're perpendicular, right? Okay, they're perpendicular. In order for us to be able to use a coordinate system, it has to be what's called an orthogonal coordinate system.
I don't like
So orthogonal is a big fancy word that you use in higher level calculus, and all it really means is perpendicular, right? So an orthogonal coordinate system is one in which all of the different coordinates, the different directions are mutually perpendicular, so they're all perpendicular to one another. So in this case, it's pretty easy. In two dimensions, there's only two dimensions, and they are, they're pretty clearly perpendicular, right? But we don't live in flatland. We live in a universe that has volume, right? So we have room for another perpendicular dimension to this. And where would that go?
Backwards and forward.
Okay, straight out of the board. Okay, so then that one we could draw like this. It's going to kind of come out, and then as it disappears into the board, I'll make it dashed, right? But it's coming out of the board at us. Make sense? Okay. So it's like it's coming out of the board this direction, right? Coming at you.
like that. There's a
So-
little.
It's
Oh, I'm sorry.
you see what I'm saying? It's hard to draw because I'm drawing it on a two-dimensional surface, and so I've got to kind of be tricky with my drawing. But really, what I mean by this, what's being implied when I draw this arrow coming out of the board like this, is that it's coming straight out of the board. Okay, and this is going to be what we call the z-axis. And notice that it too it's perpendicular to the other two. So, for example, maybe this helps if I do that. So it's perpendicular to the x-axis. There's a plane here, like a tabletop, right? And the z-axis looking straight down from above, we'd see that the z-axis is perpendicular to the x-axis. And if I look kind of from over here, I would see a plane, like a big window coming out of the board. And on that one, I would see the y-axis vertically and the z-axis horizontally. And so once again, in that plane, they're also at right angles. Agreed? So we could say that, yeah, this is an orthogonal, three-dimensional coordinate system, right? It's an orthogonal three-space where I've got room for three separate vectors or axes, we'll just say for now, that are all mutually perpendicular. So they're all perpendicular to each other, okay? Where's the fourth one go? Okay, and you're right, that's the look I would expect, Katie, because is there room for a fourth one?
I mean,
No.
There's not room for a fourth orthogonal vector, right? There isn't room in our universe to make a fourth line there that's going to be perpendicular to all of the other three. Okay. What would be required for that to happen? For that to happen, what would be required is that our universe had 4 extended dimensions, but it only has 3. So is it possible that could there be, as most modern physicists are starting to think that perhaps our universe is just like it's a little anomaly in the Algebraically field, that it's just what we call a bubble universe. It's embedded in a higher multiverse.
What are you talking about?
We'll talk more about that
What
later.
kind of inflate
So what it means then, just in a nutshell. Now,
I don't like
listen,
that.
you guys have to raise hands. We can't, because I gotta talk and then you're gonna have to talk like one at a time, so you gotta raise hands. So a lot of, the big time cosmologists now are suggesting that probably our universe is just, it's one universe embedded in a multiverse with other universes too. I mean, ours, even if ours looks infinite from the inside, it may not from the outside, as being embedded in whatever space it's embedded in, probably different dimensionality. But the point I'm making here is, we'll go off on this tangent some other time, I promise you. But the point is, there could be other bubble universes, different than ours, that have different numbers of extended dimensions. Like there could realistically be.
You're making my brain hurt, please.
Okay, you gotta raise hands.
hey.
You gotta raise hands. If you're gonna talk, you absolutely have to raise hands.
Can we just get my scales real quick?
Hey, we all gotta do this. We gotta play the same game. This isn't gonna work. We can't have these fun discussions if we can't be organized about it. So, do you have a question, Katie? You can, it's fine. I mean, well, I'll take a few right now, and then I wanna, but anyway, the point is that and I don't wanna, I just wanna give you kind of a reason for thinking about dimensionality here a little bit, right? So the idea is that some of these other universes in the multiverse, they could easily be 4-dimensional universes where they've got 4 extended dimensions. Now, you have no idea what that could look like, because, and nor do I, nor does anybody, because there's no room in our universe for that extra dimension. But does that mean there couldn't be? Absolutely not. There could be. There are mathematical spaces where you can have 4 different axes that are all mutually orthogonal. Yes, sir.
So, if you just thought, so you'll add up, if you just were able to keep going away from the deal, you make it to a different one, or would you never leave?
It's, for several reasons, I'm gonna say you can't leave, but the principal one being that the universe is expanding, the boundaries of the universe are expanding faster than the speed of light from our perspective, so you could never get to the edge, even if there was. But probably there isn't. So you're probably, once you're in a universe, you're stuck there, but, yeah, weird concept.
What if it's just a circle
Wait.
like Earth, like you know how they thought that you walk to the edge of Earth?
Yeah, you fall off.
Yeah, like what if it's just.
Well, there's all different, I mean, I could talk about this for a month. I mean, you could talk about, there's multiple connectedness, you can look at different, but anyway, we can't go off on that tangent today, because I actually want to get something done today. So last question, yes,
I
ma'am.
think we just did.
Mhm. So, I mean, it's really, it's almost like you can't, sometimes you run into this in physics. You run into the idea that we have models that work pretty well, right? Now, this is the last I'll say about this, but I think it's important to say. So like when we want to talk about an atom, you guys talk about atoms a lot in physical science and in chemistry, right? Well, what does an atom look like? Okay, raise your hand. Somebody help me out here. What's an atom look like? You mean?
It's like a little cloud.
Okay, it looks like a little cloud maybe, right? Well, Not really.
Well, yeah.
It doesn't really look like anything. Does it actually have, like, there's some models, if you go back to some of the earlier models that are very, very useful, you can treat an atom like having little discrete electrons that are orbiting around a nucleus, and their orbits are determining the energy levels, right?
Yeah.
Extremely useful model, has no bearing on reality whatsoever, but who cares, right? At some point, the models serve their purpose, and the fact of the matter is, you can never see an atom. When you get down to that level, quantum mechanics gets so bizarre that if you could shrink yourself down, like here's that movie that, we guys listen to.
Yeah.
I know what I'm talking about. So, anyway, if you were able to do that, but just keep on shrinking, so you got down to a level where you could like interact with atoms and things,
But then what
it
would-
wouldn't work, because you couldn't possibly be a person at that level, because your body wouldn't stay even self-contained. Particles in your body would be jumping all over the place, and what you'd become is a part of the Schrodinger model, Schrodinger wave. You'd just be, statistically, there's a certain chance that parts of your body would be here and there, and you wouldn't be, it'd just be different, right? It'd be so dramatically different that you couldn't really parse that with your everyday macroscopic reality, right? So there are some things that you just can't, we just want to know, what's that look like? It doesn't look like anything. Atoms are smaller than the wavelengths of the light that we use to see things, and so they don't look like anything, right? They really don't. We can kind of look at what an atom, we can take, really fine-grained positron imagery from a scanning positron microscope, and we can see it's a type of microscope that gives you extremely high levels of magnification. But even then, you're just getting kind of a blurry image of like what it would look like to us if it were a visual thing. Point is, none of this stuff is real, right? It's stuff that's real. There are atoms here, but it's not something that you can ever experience in a way that's going to make sense to you, right? And in that sense, you talk about things like multiverse theory, and you're starting to talk about these entities that are higher dimensional entities. They're surfaces. Like imagine a surface that's more. The surface of a ball is two-dimensional, right? But if you talk about higher dimensional entities, surfaces can be more than 2 dimensions. It gets really bizarre. You get into string theory, it gets extremely bizarre, and so to think that there's some kind of a way that you can conceptualize this in a way that's meaningful, it's kind of this doesn't work. You just can't. It's not like you can simplify this down to something that's going to make a lot of sense. That happens a lot in math and physics at some point. But you just got to kind of abandon that way of thinking about it, and instead just try to find models that are predictive, models that give you reliable answers, right? Reliable predictions. And if you do, then those are good models. Okay? So let's go back to this problem. If we have time at the end, I'll show you a picture of a tesseract. I've moved it up.
Do that, please.
So if at the end of class, if we have time, I'll kind of show you what the shadow of a hyperdimensional cube looks like. That's kind of
Maybe
interesting.
we should come in during fifth period.
So let's get going. There's your motivation. Let's get going. Okay, so then,
Okay, we're listening now.
okay,
Thank you.
so let's take this equation. Now, how did we do? There's something really interesting we can do here with this that if this is going to resonate with some talks we had last week. Like if we want to define x-intercepts, for example, or y-intercepts in the xy plane, how do I find an x-intercept?
I don't know.
What did I do? Like if I've got the
You made
line,
x equals something y plus.
so what if I've got 2x plus 4y equals
You
Uh,
said y to 0.
equals 9? And I want to solve for the x-intercept, what do I do?
So y.
I set y equal to 0 and solve for x, right? And that's going to, everybody agree with that? That's going to give me the x-intercept and vice versa for the y-intercept.
Can you do that, please?
So if I want to do something, what if I want to find the intersection of this 3-dimensional thing up here that we got going, right? If I want to find the intersection of that with the xy plane, what do you think I would do?
Same thing with each variable.
Okay, raise your hands. I need hands. Yes, ma'am.
The same thing with each variable, you like set one variable to equal the rest of it.
Okay, that's a small step in the right direction, but if I want to find the intersection with the xy plane, what do you think?
Set z to 0.
Set z to 0, right? Because what is z telling you? Now think what, instead of an ordered pair now, we got an ordered triple. Like, let's say I'm gonna draw with my three-dimensional pen. It is a three-dimensional pen, but pretend I've got a three-dimensional board up here that I can draw points on. Okay, this is pretty slick. This is next level stuff. Our district, really, the budgets have improved a little bit. So I wanna draw a point, I'm gonna draw a point here in space. I wanna draw a point at the ordered triple, 2, 3, 5.
Can you draw it in there?
What does that mean? I'm gonna have to, aren't I? What's that mean?
So that's X, Y, Z, right?
Right. So I'm gonna go over 2 to the right, agreed?
Up 3.
Up 3,
And out 5.
out 5, there it is right there.
Nice.
Okay, you get the idea?
Wow.
Okay. So then if I wanna find the intersection of this three-dimensional thing with the XY plane, I just need to make the Z coordinate 0, don't I? Because I wanna stay on the board. I don't wanna go out of the board or into the board, right? You get the idea?
Yeah.
Okay, so if I said,
That makes sense.
Oh.
if I said Z equal to 0, what do I get? Well, I just get the line 2x minus 6y equals -8, right? And that's one, we can graph that, right?
Yes.
Let's find 2 points and connect and extend. If I set, for example, y equal to 0, what's x? -4. Okay, so 1, 2, 3, 4. So there's 1 point. If I set x equal to 0, y is 4/3. Okay, so that's gonna be just right about there. And so this purple line is gonna be the intersection of this three-dimensional thing and the XY plane. That's what the intersection is, right? So would anybody wanna propose what this thing actually is then?
I'm
Okay,
so
so now, hold on. So if the intersection, right, of this three-dimensional thing, and we're trying to figure out what the heck it is, right? The intersection of this three-dimensional thing is that purple line. What is, I mean, what in the world could intersect the XY plane and have the intersection look like a line? When I intersect 2 lines, what do they intersect in?
I don't know.
A point, right? Okay, so what could it be? Could be a plane. Could be a plane, right?
Don't mean an airplane.
I don't mean an airplane, no. Right, I mean, it could be an infinite flat two-dimensional surface, and it cuts through the XY plane, and it makes that cut through the XY plane, right? Now, if I want to figure out what kind of cuts does it make in the other planes, like if I want to figure out what's its intersection with the YZ plane, I would just set x equal to 0 and solve. And I would have some line out here in that plane that's, right, you see what I'm saying?
Yeah.
And if I want to figure out what's its intersection with the XZ plane, I could set y equal to 0 and solve, right? In each one of those cases, the intersection is going to be a line. Agreed? Okay, so now we're getting someplace with this, aren't we? So we figured out that when I write a linear equation in 3 variables, the geometrical entity that we're talking about is not a line, it's a plane. Okay, it's a plane. So then when I look at a system like this, I've got 3 different equations in 3 variables. Each of them has 3 variables. So each one of these is a plane, right? Now you got really, your brain's gonna hurt at the end of the day today.
It's
So-
already.
So I wanna know then, what could the intersection of 3 planes look like? Okay, it could be a point, right? And in the cases we're interested in, you know,
Wait.
we're gonna hopefully, like, we're gonna culminate this with looking at some applications, right? We'd really like to be able to solve a linear system and get specific values for x and y and z, right? Sure, yeah, well, let's talk about that. Let's talk about, we're gonna go back and do a quick geometry review, right? So, real quick, what's a point? A point is how many dimensions does a point have?
1,
No?
3, 1.
Zero.
What?
A point is a zero-dimensional, that's just a zero-dimensional thing in math, right? Does it have any size at all? No. A point is vanishingly small. Okay, what's a line? No.
One dimensional.
One
It's just
dimensional.
flat.
A line is one-dimensional. It's only got length, right? It doesn't have any width in it. Now, if I cut through a line, it looks like a point, right? So a plane is two-dimensional. A plane is like if I were to extend my whiteboard forever, that would be a plane. If it was infinite in all directions, that would be a plane, right?
It's just a flat.
So a plane's got two dimensions because it takes an x-axis and a y-axis to be able to orient yourself in a plane. And then what would be bigger than a plane?
Everything.
Well, we call it a space, right?
Yeah.
Maybe a volume would be another way to say it. Right?
Because it's like
Where
one,
you've got three extended dimensions.
Three.
Yes, Jim?
So then the intercept should look like just a single point in like an infinite amount of space pretty much then, right?
Right, so give me an example,
Plane.
like if we say that, now we can't see it, planes are infinite, right? But we could say that the ceiling of this room is a representation of, at least it's a piece of an infinite plane. Assume it just goes forever, right? Okay, so their ceiling is one plane. Let's say that the back wall of the room is another plane. Can you see that the intersection of those two planes, the joint where they intersect is going to be that line between the back wall and the ceiling?
Yeah.
Agreed? So two planes, if they intersect, will always intersect in a line, won't they? Could you have parallel planes?
yeah.
Ceiling and floor, for example, right? If we extend those forever, they would never meet, right? And so there would be a case where that'd be equivalent to like parallel lines in two dimensions, right? Okay, but now can you give me an example of where, just thinking about it in the room here, can you give me an example where we get three different planes that intersect at a point? Ah, a corner. There we go, right? So we got the front wall, we got the ceiling, and we got the side wall, and they all intersect at one point, right? So there's an example of where you'd get a 3x3 linear system, three variables, three linear equations that have one single solution. It's going to be the coordinates of the point of intersection, okay? But things could go wrong. I won't say wrong, this isn't necessarily bad, but sometimes we may not get a single solution. Like if we were going to take the planes, like the ceiling of this, the ceiling and the floor, and maybe the floor of the hall below us, right? Those would be three parallel planes that obviously would never intersect, right? Or what if we did something like, how about this one? What if we did this wall of the room and the ceiling of the room and maybe the floor of the room? All three of those never intersect at the same time, correct? Okay. Or how about this one? What if we did this wall and the ceiling, and what if I did another plane that kind of cut through at an angle that also cut through that same line? Then there would be an example where we'd have three planes that intersected in a line, so there were an infinite number of solutions to that system, right? So there are possibilities for us to get either zero solutions or infinite solutions when we have three variables in a 3x3 linear system. But the ones we're most interested in real life are typically the ones where there's a single solution, right? Where we get a single point. Okay, get the idea? Okay. So now let's kind of explore some ways that we can just do the algebra, and then we'll come back to the geometry of this a little bit later. When are we out here? 10. Okay. So let's just make sure we at least know how to solve a system. And then once we get that down, I'll throw some other weird stuff at you. It's interesting.
Yay.
So there is a technique for this. If we've got a 3x3 linear system, there's a relatively simple way to solve these things algebraically. So what we do is we're gonna pick two pairs of two equations, and we're gonna pick those so that we can eliminate the same variable from both sets, right? So like here, for example, what would be an easy variable to eliminate? Probably y, it looks like. Okay.
So the bottom two.
So, because in the bottom two, it's really easy, isn't it, right?
Yeah.
So then we could do something like this. We could say, let's go ahead and set up this system right here. These two we're going to combine, and we're going to call that A. That's going to be system A. And these two right here we're going to combine, and that's going to be B, right? And we're going to solve those. We're going to eliminate the same variable from both of those, right? And then we'll see what happens when we do that. So let's start with A. If we want to eliminate, we've already chosen to eliminate the variable y, correct?
Yeah.
Okay, so what do I have to do then in this one? Let's rewrite system A over here. It's 2x minus 6y plus 9z equals negative a. 5x plus y plus 2z equals 10. So what would I have to do to be able to set that up to eliminate the y's? Multiply the bottom one by 6. Good. So we'll do this. Right?
Would it be negative 6?
No, it'd be 6 because we want to add those up so they add to 0, right? So then what's that give us? If we do that, that gives us the new system 2x minus 6y plus 9z equals negative 8. And if I distribute the 6 all the way through here, you guys help me out. What am I going to get?
30x plus 6y plus 12z equals.
Okay? And then if I add those vertically, we get the y's to cancel, and look what comes out of that. I get the equation 32x plus 17z, 21 I mean, what am I, phew. I don't know, too much talk about hypercubes on this. 21z equals 52, okay? So there's one equation we get, right? Now, what are the variables in that one? X and Z, okay. So now we gotta go back over to system B, and we're gonna write down system B. That's 5x plus y plus 2z equals 10, and 3x plus y minus 8z equals negative 28. What do I have to do there to get the y's to cancel? Okay, so we'll just distribute a negative through the bottom one, okay, and that's going to give us, then we get 5x plus y plus 2z equals 10, and what, negative 3x minus y plus 8z equals 28, and if we add those up, the y's cancel, which was our goal, and we get the equation 2x plus 10z equals 38. Okay, how come? Why'd we do all that stuff? Okay, if we take these two together, right? Yeah, if we take those two together, now look, what we've got is, we've got a collapsed system here now, right? Now we've kind of evolved this down to a point where now we've got a simple 2x2 system that's a piece of cake. And the 2x2 system is going to give us back, when I solve this 2x2 system, that's what you've been doing already, right? We're going to solve for x and y, then what would I have to do to find z?
We're gonna solve for X and Z this week.
If once I know what x and y are, how can I find z?
Just
Plug it
Just
in.
plug it into any one of those equations and find z, right?
wait, are you finding?
So are you doing elimination?
Can you finish it out?
Yeah, we're going to. Yeah, we're going to. So we got, quick summary though, so we make sure we know where we are. So we decided to get rid of y. We used the top two equations in system A, bottom two equations in system B, and we solved those. Okay, now we're going to take both of those, and notice the red and the blue is going to make purple, right? So we're going to get, how about that? 2x plus 10z equals 38, and 32x plus 21z equals 52. So we probably want to use elimination, wouldn't we? So what could we multiply by here to make this work?
Negative 16.
Negative 16. So the top one, we'll distribute a negative 16 through, and that's going to give us, when we do all that, we're going to get negative 32x minus 160z equals, oh boy, what's that going to be?
Big stupid number.
Negative 832.
Okay, and then I get a 32x plus 21z equals 52. And when I add those up, the x's cancel. And then what am I going to get here? So I get negative 139z.
Negative 780.
780.
Okay, and what happens then if I divide both sides by negative 139?
Decimal.
I do?
Yeah.
Can you put it in a fraction?
I shouldn't have, so we did something wrong here.
I think negative 16 times 38.
Super easy to find.
Come on.
Negative 16 times 38.
Yeah, it's 608.
What's going on?
608 on the equation method of negative 16
Yeah,
times
yeah.
38.
That one? There we go. Okay.
So what is it?
Okay, so there's our mistake. So that should have been, that's gonna impact this.
So that turns into.
So that should have been a negative 608, you said?
Yeah.
Okay, so then that's gonna become
Negative 5.
556? Okay, now that's gonna work too. So negative 556 divided by 139 is gonna be 4. So z is 4. So what do I have to do to find x? Well, let's plug it back into, how about that one? That looks a little easier, doesn't it?
Yeah.
Right, so I could feed the z
So it's
back
gonna
into
be
there to
negative
find
4.
x. Agreed?
X is negative 1, I think.
So what's that give me then? That gives me 2x plus 10 times 4 equals 38. So that's a 40, so I get 2x equals negative 2. So x equals negative 1. Agreed?
Yes.
Okay, now I've got x and z. So now all I got to do is go back up here and let's pick the easiest one. Like, how about this guy right here?
You gotta
And we're going to plug those values in for x and z and solve for y. So it was 5 times 4 plus y
equals 7.
plus 2 times negative 1 equals 10. So what's that give me? 20,
Oh,
18.
You got
Your
the
variables
mix
mixed
up.
up.
Mixed up.
Did I mix them up?
Yeah.
Sure works.
Oh, I did? Oh, that's
It's
bad.
5 times negative, or 5 times negative.
Okay, let's fix that. So the x was the negative 1, is that right?
Yep.
Z was the 4? Okay, so I'm gonna get negative 5 and 8, so that's 3, so I get 7?
I can't.
This problem is.
Okay, everybody agree? I hope I did that right, but I'm just trying to go fast. So now we got x, y, and z, so how would we write our answer? We'd write our answer as an ordered triple. So our answer is gonna be x was negative 1, z was, y was 7, and z was 4, right? There it is.
That was a lot.
Okay.
Yeah, right? Okay, so that's the process, right? That's the process, yes, sir.
So they use like dimensions and coordinates to find like how far something is in space.
Yes, yeah.
Could you use time as a different dimension?
You actually have to, right? Because, so it's a very good question. So when we, in physics, we talk about, we'll go ahead and just the last little bit here. You guys, you know how to do that, right? You get some practice on that. Okay. Oh, yeah. Let me show you the tesseract and then I'll take your questions. Good question.
Please don't, please don't. You're gonna make my brain hurt, please.
That works.